Lecture 16, Part B. During this part of the lecture, I'll be looking at solutions to the initial value problem of the 1D heat equation. However, before I do that, I'm going to introduce a few preliminaries or ideas with respect to the Dirac Delta distribution. So before we start, remember in the Part A of this of Lecture 16, we found the solution to the heat equation, the self-similar solution, and we found that it had roughly this profile. For t very small, it was almost an infinitely high spike, and as time went on, it just decayed as the heat was no longer so concentrated at a point, and then just moved out into the medium. So the self-similar solution basically with time represents the solution that starts at time equal to 0 at something that actually shoots up to infinity. So all the heat is concentrated at one point. The areas of all these graphs are the same, so the total amount of heat is conserved. But as time goes on, that heat flows into the surrounding medium, becomes flatter and flatter and more distributed throughout the medium. So what I want to do before we go on and find the solution to the full initial value problem, and we are going to use a self-similar solution to do so, is look at the properties of the Dirac Delta function a little bit more rigorously. So firstly, this Dirac Delta distribution, and it's not a function, apologies, was introduced by Paul Dirac. The reason is that Paul Dirac is a very good mathematical physicist, and the reason he introduced it was he was trying to model electrons, okay? And it was basically, he wanted to model the density of a very, very idealized point mass or charge, where all the mass and charge is confined to a single point and yet has a finite mass or charge associated with it. And to do that, he described the following distribution, which is basically the Dirac Delta distribution. He said, let Dirac Delta have the following properties. It is equals to 0 for all x not equals to 0. However, if x is equals to 0, it is equals to infinity. But it has the additional constraint that it describes something with finite mass, and all that mass was normalized to 1. So you constrain this function delta by this integral, saying that from minus infinity to infinity, delta of x dx is equals to 1. Okay, and even though no function, as I said previously and several times, is not a function, there's no function that can have these properties. But even though that is true, it is possible to write this distribution of a limit of normal functions. Okay, as a limit of normal functions. And basically what we do is write down a series of functions with a parameter and then take the limit as the parameter approaches 0. So to do that, let's give one example of these series functions, and to do that I'm going to simply define delta a of x equals to e to the minus x over a squared of the absolute value of a, and in fact this represents the functions plotted here. Okay, so it's roughly Gaussian distributions where a is associated with the mean, but it is also not the mean, the standard deviation, but it's not quite. You can then show that as a goes to 0, this thing, which is plotted over here, becomes more and more spiked. Okay, and then eventually in the limit where a is 0, it becomes the Dirac Delta function. Okay, and you can see that directly simply from looking at the graph, but also you're at the formula. Suppose x is not 0, then you have an exponent of something squared, where the denominator, which becomes very, very large and very negative, and over a, which is 0. However, this thing converges to 0 so rapidly that delta a of x then is 0 or approaches 0. If, however, x is 0, then the exponent in the numerator is simply 1 divided by a, which approaches 0, so it becomes infinite. Okay, and this, as I've said, you can see by looking at the function. The series is not unique. There are other series or other choices of functions that will actually give you the same Dirac Delta distribution in the limit. and regardless of the series that's used to describe it, you don't, for most part, don't even need a series at all, as long as you always keep the distribution inside an integral sign. But part of the properties of distribution is firstly a scaling property. Delta of alpha x is equals to x over the absolute value of alpha. And the second property that we'll use in the next slide is the convolution property. Basically, delta of x minus a specific x of f of x integrated over x is simply the function evaluated at a specific x. Another thing that should be observed with these sort of with a series of functions that approach this, the Dirac Delta function, is when we sort of connect it with the heat equation. Remember, it's a self-similar solution. So at time 0, we effectively have a delta function, which corresponds to all the heat being concentrated at x equals to 0. And as we showed previously, the heat is finite and constant. And then as time marches on, that heat certainly just dissipates or flows into the rest of the medium with a specific profile described by the normal distribution. So that gives you a very intuitive feel for what the solutions to the heat, or self-similar solutions to the heat equations do. Just to be complete, I want to introduce an associated function, basically the error function, that's roughly associated with the area underneath this Dirac Delta distribution. And to do that, let's introduce the Gauss error function. And when it's simply defined as 1 over the square root of pi, the integral from 0 to x, e to the minus t squared dt. And I should say that the definitions I've used here are sort of the standard definitions used everywhere. If you ask for the mathematic to give you an error function or any other software program, this is the definition that they'd be working from. Similarly, when you have algebraic computer algebra problems, you're working with a delta function, they will know it's not a function but a distribution, and these properties will be programmed in. So the Gaussian error function arises in probability, mainly in the theory or the analysis of errors, and it was first introduced by Glaisher in 1871. So it's been around for a long time. One of the first properties that you can verify just by looking above is that its derivative is simply 1 over pi e to the minus x squared. Okay, so now to connect it directly to the series of functions that ultimately leads to delta functions, which are also the series of functions that characterize the solutions to the self-similar solution to the heat equation, is let h of a be equals to the integral of minus infinity to x of delta a of z. Okay, so to evaluate this, substitute in delta a of z, basically this expression over here. Okay, make a change of variables to say x prime equals to x over a. In other words, that you could basically write the integrand in this form over here. And if you do that, you can then you then have an integral of the derivative of something, and the answer basically just becomes that it's the error function of x over a, because x prime is equals to x over a, where you have fixed the this changing the variable introduces a factor of 1 over a as well, so that cancels out, and you're just left with this integral being equals to a half the error function of x over a to be evaluated at minus infinity and x. Now the error function evaluated at minus infinity is simply, because e to the t squared is symmetrical about x equals 0, simply the error of this thing evaluated at minus infinity, so it's equals to minus this thing at evaluated infinity, but you're subtracting it, so it is minus minus this guy evaluated infinity, and for it to be evaluated infinity, it's just the total area under this graph, e to the minus t, which is 1. So you basically have a half from the minus term plus a half times the error function evaluated at x over a. Okay, so there's a clear connection between the area under these delta A series that eventually limits to the delta function and the error function, and it's given by this expression. Okay, another thing that's interesting to note is we've shown that the delta function going to be given as the limit of a series of the delta distribution, so it's going to be given as the limit of series of functions, and similarly, so the Heaviside function h of x we can also define as the limit as a goes to 0 of h of a of x. Okay, and that is just 0 and 1 if x is less than 0, and sorry, it's just 0 if x is less than 0 and 1 if x is greater than or equals to 0. And to see how that arises, let's just look at it graphically, but you can also do it entirely rigorously. Here I've plotted basically the area. I've basically plotted h of a for corresponding a's of corresponding colors. So for example, if a becomes very small, this delta function or this normal distribution becomes very peaked, and the area underneath transitions from 0 quite rapidly to 1 up here. Whereas if a is larger, the distribution is less peaked and this transition happens more slowly. However, in the limit where a goes to 0, this thing becomes infinitely peaked and the transition happens exactly at x equals to 0. Okay, so that's a useful way of simply showing that the Heaviside step function is just the integral of the Dirac Delta distribution by simply showing that it can be expressed as the series of the integrals of the functions that eventually limit the Dirac Delta function itself. Okay, given this background, let us now go ahead and solve the initial value problem on an infinite domain. So firstly, the initial value problem in its full formulation is just the heat equation or the diffusion equation in 1D on the domain minus infinity is less than x is less than infinity, for t greater than 0, and we want to specify u of t equals to 0 equals gx. Okay, so that's what we call the initial value problem. And as I sort of indicated in part A, we're going to start constructing the solution out of self-similar solutions. So observe that the self-similar solution we derived in part A is simply us of x and t equals to 1 over the 2 times the square root of pi kappa t, the exponent of x squared over 4 kappa t. And using the functions we've just been talking about in the definition of the delta function, or in the series that limits the delta distribution, we can express this as delta A of x, where A is now equal to 2k kappa t. So you can then immediately see as t goes to 0, u of s, the self-similar solution, goes to, A goes to 0, and therefore u of s of s, approaching it from the positive, approaches the delta distribution at x. So the self-solution is basically a solution where all your heat at t equals to 0 is concentrated on a point that has area 1. And then as time goes on, that point sort of flows into the thing in the shape of a normal distribution that becomes flatter and flatter and flatter. Okay, however, the fact that this self-similar solution is equal to a delta function on the boundary actually makes it very easy to write down the solutions to the heat equation given a general definition on the boundary. And you can intuitively see how it happens. Suppose you would have a whole bunch of self-solutions that at each point represents the heat at that, is multiplied by the heat at that point. Then you can simply have that, because the solution is linear, those solutions should just add, and you can simply have each point's heat then dispersing into the surrounding medium in a self-consistent way. And similarly, if you were to have dye at each point just diffuse into the medium, you could also show it as a combination of self-similar solution with a dye at each point, the concentration flows into the medium. And the way to express that mathematically is just to observe the following. Okay, so on the boundary, we can just express the boundary conditions as follows. We can simply say u of t is equal to g of x, but that we can rewrite as g of y integrated over the whole domain that multiplies delta of x minus y dy, just using the convolution property discussed in on the previous slide. And that we can write, because we know delta y is simply the self-solution at times t0, we can simply write it like this. Okay, and once you've done that, it's a reasonable question to ask, well, it works for the, at time t equals to 0, why don't we just put in times t over there and try and write that down as the solution for the whole problem, because effectively this is a self-similar solution that's just been moved on the y-axis. So the point at which the concentration of heat starts has been moved, but that will make no difference to the self-similar solution's derivatives with respect to x, or with respect to t, in fact. So basically, here's the question: does u of x and t, which is equals to the convolution of g of y with the self-similar solution now for all of t, satisfy the heat equation in general? And that basically requirement would be met if you could show that u of t minus kappa uxx is equals to kappa uxx for all of t. Okay, and the answer is yes, it does. And the reason it does is because these solutions you're convolving it with satisfy the heat equation on the domain, and because it's a linear problem. It only works because it's a linear problem. Okay, so let's just show it explicitly. So to show it explicitly is take the derivative of u, or apply the heat equation's operator to u, and we want to show that this thing is equals to 0. And the way we do that is these derivatives, the only function of x and t is simply the self-similar solution, because we're integrating over the y variable. So we can move, and because that integral we assume converges, and it will converge provided g converges, we can simply move this differential operator into the integral, because the integral is effectively constant as well, so we don't have to be careful about the boundaries. We have g of y, which we could potentially move outward, multiplying dt minus kappa dxx us of x minus t, which we've already shown obeys the heat equation, and this just moving it by a constant factor makes no difference at all. So because it doesn't influence the derivative operator, so you can basically show that this thing is equals to 0, and if you're uncomfortable with this extra y, simply put in x minus y into this expression and actually do the derivatives yourself explicitly, and you'll find that it is 0. Okay, so that's equals to 0. So yes, we now have a solution to the initial value problem, and that solution can be described as this: simply the value on the initial data slice, in other words t equals to 0, divided by 2 pi kappa t, multiplied with the exponent of x minus y, the point at which the function is being evaluated on the additional data slice, over 4 kappa t dy from 0 to infinity. Okay, and that solution is valid for all x and all t, provided t is greater than 0. And intuitively, it also works very nicely, because it's basically at each point on the initial slice, you're multiplying the heat and letting it diffuse in the manner of a self-similar solution into the medium, and it's just that the heat, they add up as time goes on until it eventually becomes a very flat profile. Okay, so it's a very nice intuitive solution. Another thing you should also just see by looking at the structure is, once again, we've written the solution as an integral of the initial data multiplied by something that looks like a Green's function. And in fact it is. What we have not yet done in this lecture, and what we'll most probably do in the next one, is shown that this is the unique solution. Okay, so similarly to the way in which we handled Laplace's equation, where we first found the solution and later showed it was a unique solution and it had certain properties, we'll now go ahead and work out all the similar properties for the heat equation as well. But that is Lecture 17's problem. Thank you very much for listening. That's gone.